And my name is Jason Petta. I'm a professor of physics at Princeton University, and my research is focused on quantum control of nanometer scale systems. Basically, in a nutshell, what we do is we take small pieces of semiconductor and we isolate single electrons in what's called a quantum dot. It's a box that electrons trapped in, and we control the spin degree of freedom of that electron. You can kind of think of the electron as a spinning top. You can spin it, either clockwise or counterclockwise. And those two states of rotation of the electron spin can be used to encode a state of a qubit, whether it's state 0 or 1. I think the main thing that's generally called out in the context of quantum computing is factorization of large numbers and cracking RSA encryption, things of these nature. Generally, it's believed will require a large number of qubits. I think that in addition to traditional approach of just pursuing large-scale quantum computing, there are other ideas of using quantum systems for other processes. Like recently, it's been shown that you can use handfuls of qubits or 10, say roughly qubits, to simulate ground state energies of molecules, look at things like chemistry and chemical reactions. I think it's interesting, sort of smaller scale. And there's even important things that can be done at the level of single qubits, using qubits as quantum sensors to probe local magnetic fields or temperatures or electric fields. I see this as a whole area of quantum technologies, and brute force quantum computing to factor a big number is one small part of the entire picture. Yeah, I think if we look back collectively at how far we've come, I think a pretty big distance has been traveled. I mean, the early experiments in this field demonstrating quantum coherence in semiconductor or superconducting systems were performed in the late 90s, and at that stage we could only see a few coherent oscillations of the quantum system, and the coherence just persisted for a nanosecond or two. And the materials, the technology has come a long ways in the past 10, 15 years, and now we have systems that routinely, say for superconducting qubits, can have lifetimes that are tens of microseconds. They're mini qubit processors that are being developed now in industry, and so there's been a lot of progress in the field. But still, to make a realistic quantum computer that can factor a number and compete with today's classical computing technology is a ways off, and it's hard to extrapolate between here and there. I think there are two things that give quantum computers their special power that go beyond classical computers. I mean, the first thing at the heart of it is the idea of superposition, that we can have a quantum system. It can either be in ground state or the excited state 0 or 1, or we can make a complex superposition of those two states. Another thing that's important is parallelism. If you take a few qubits and make them interact, you'll have a highly entangled state, and that allows you to perform certain types of computation more efficiently than you can do with a classical computer, having access to this very large kind of state space. My feeling is that in this community of quantum information science and technology, there are a whole lot of different roles that need to be addressed. And at the academic level, I see us as doing the first demonstrations, proving that we can make qubits, we can implement few qubit operations, improving materials, looking at long-term challenges in the basic fundamental science. I see that being done in academic research groups. To really make a quantum computer, to make thousands or 10,000 or a million qubits, to make something that's fault tolerant, to me that feels like more of an industrial or national lab scale kind of problem, where we need people who can address the microwave control electronics, the DC electronics. There's a whole higher level picture of just the coding and the software that's going to run the hardware of the quantum computer. And it feels like it's going to be more than just an academic effort at some stage. And you see the beginnings of that now with input and financial support from Microsoft and Intel and other companies kind of starting to jump in the game. I mean, normal people don't have access to supercomputers. Even big academic research groups don't have their own supercomputer. These things are done at large-scale facilities, and you sort of buy in time to gain access to these resources. And my expectation, at least in the short term, the next 5 or so years, you're going to see more of a mode of operation like IBM has taken, where a small quantum computer consisting of maybe 5 or 20 qubits is brought off the ground to get this thing running, and it's open to public and other industrial use, maybe at cost. I think that will be the mode of operation. Based on a lot of the technical requirements associated with getting these types of experiments and systems kind of up and running and off the ground, I doubt that we're going to see these in every household in the near future.